Let's jump right into this explainer. Today, we're unpacking the magic and, honestly, the intense math behind achieving near-photorealistic graphics in real time. We're going to look closely at a groundbreaking experiment by Electronic Arts called Pika Pika to demystify exactly how next-generation engines are lighting up their digital worlds.
The ultimate hurdle in modern computer graphics is perfectly summed up by these beautifully lit little robots. How exactly do we take movie-quality path-traced graphics, the kind that usually takes massive server farms hours to render a single frame, and somehow make them run fast enough for live, interactive gameplay at a smooth 60 frames per second? It is a monumental challenge.
So, here is our roadmap. We'll start with the real-time rendering challenge, move into the hybrid pipeline solution, dive deep into mastering ray-traced shadows and solving real-time reflections, before finally wrapping up with the future of AAA gaming.
All right, part 1, the real-time rendering challenge. Let's tackle the foundational hurdle every developer hits when trying to make a digital world look truly real. Ultimately, what we're all chasing is the breathtaking physical accuracy of offline path tracing, where light actually bounces and scatters exactly like it does in the real world. But real-time hardware constraints have historically forced the industry to rely on traditional rasterization. Sure, rasterization is blazing fast, but it heavily relies on smoke and mirrors to fake that lighting, which severely limits visual fidelity. We desperately needed a way to bridge this massive gap.
Moving on to Section 2. Let's explore the hybrid pipeline solution. This is the clever, big idea the engineers behind Pika Pika utilized to bring these two completely different worlds together.
The brilliant realization here is that we literally don't have to choose between the old and the new. We can use a hybrid approach. Think of it kind of like a relay race. By letting each graphical stage do exactly what it does best, the rendering process becomes highly compartmentalized. We leverage the raw speed of rasterization where it makes sense, and then surgically inject the stunning accuracy of ray tracing only where it truly matters.
It's fascinating because we actually aren't ray tracing everything. The basic scene layout and geometry, often referred to as the G-buffer, is still completely handled by standard rasterization. Then compute shaders step in to take care of direct lighting. It's really only the incredibly complex visual features, like global illumination and transparency, that fully rely on ray tracing. By sharing the heavy lifting across these distinct stages, developers unlock incredibly scalable performance.
Now for Section 3, Mastering Ray-Traced Shadows. Let's take a highly technical deep dive to see how this hybrid pipeline handles one of the absolute hardest things in computer graphics.
Just look at the insane leap in quality here. Compare those simple, harsh, jagged, hard shadows we all used to settle for with the ultra-realistic, contact-hardening soft shadows made possible by ray tracing. By launching rays from a surface toward the light source in a cone shape, developers perfectly mimic real-world lighting. And naturally, the wider you make that cone, the softer and more realistic the shadow becomes.
But there is a massive catch. A wider ray cone inherently creates a ton of visual noise because you're scattering those rays over a much larger area. This brings up a critical technical question. How on earth do developers achieve these beautiful soft shadows without completely tanking the game's performance by firing thousands of rays per pixel?
The answer is absolutely genius. Instead of brute forcing the problem by tracing more rays, they calculate just a few pixels, which initially gives you a really noisy, speckled mess. But then, they apply a spatiotemporal variance-guided filter, or SVGF for short. Think of this filter as a highly intelligent digital smudge tool that magically blends and cleans up that noise temporally across multiple frames. The result? A pristine, smooth shadow. It's a perfect example of smart optimization replacing raw computational brute force.
And the pipeline even handles mind-bending, transparent shadows. Traditional rasterization completely falls apart when trying to render translucent objects like those colorful gummy bears. But with this hybrid approach, recursive ray tracing actually tracks light absorption and internal reflection right through the thick media of the object. What you get are perfectly colored, physically accurate shadows that totally ground transparent items into the scene.
Let's move to Section 4. Solving real-time reflections. We're going to explore how the Pika Pika experiment generates hyper-realistic reflections without melting your graphics card.
Older screen space reflection techniques, the ones we've relied on in games for years, break down so easily because they can literally only reflect what is currently visible on your screen.
Hybrid ray tracing, on the other hand, unlocks fully dynamic, view-dependent reflections. Just notice how the metallic surfaces perfectly reflect the surrounding world, even capturing objects that are completely out of the camera's direct view. It's a real game changer.
So, the secret to actually pulling this off comes entirely down to performance optimization. You'd probably assume this level of reflection requires a staggering amount of rays. Surprisingly, they only trace reflections at half resolution. That works out to casting just a quarter of a ray per pixel. By deliberately tracing vastly less data, they save immense amounts of processing power.
Of course, they have to turn that low-resolution data back into a pristine image, and they do that using an ingenious multi-step reconstruction pipeline. First up, material importance sampling, then ray tracing at that lower quarter resolution. Next, spatial reconstruction, and finally, temporal accumulation to seamlessly fill in all the missing gaps.
Before all that cleanup happens, the raw data is just a noisy, chaotic distribution of light. By combining material importance sampling with a rotated Halton sequence, which is basically a fancy mathematical way to scatter points evenly without creating predictable patterns, they generate a speckly but mathematically high-quality baseline. From there, the engine smooths out the data temporally and spatially over multiple frames. It's effectively performing digital alchemy to reconstruct a flawless reflection in real time.
Finally, Section 5, the future of AAA gaming. Let's zoom out and look at what this kind of compartmentalized brilliance actually means for the industry moving forward. Because this entire pipeline is built on modular blocks, developers can augment their existing rendering engines in a completely scalable way. It fits essentially any future AAA title, whether that's a heavily stylized cartoon platformer or a hyper-realistic military simulator. Developers can simply dial the ray tracing up or down based entirely on whatever hardware the player happens to be running. I'm going to leave you with this final thought to chew on. As these hybrid pipelines continue to evolve, seamlessly blending the raw, brute speed of rasterization with the stunning physical accuracy of ray tracing, how long until we literally can no longer distinguish real-time rendering from reality? As the visual line between video games and the real world disappears, you'll definitely want to keep looking closely at the shadows and reflections in your next game. Thanks for joining me on this explainer.